Okay, so it's now time for Danica to start her talk on from scene segmentation to task-based grasping.
Okay, thank you, Cecilia. Let's see if I can get up my slides. Okay, so I'll just start, and I hope you can all hear me. And many thanks for finding time for attending all our lectures. So I'm here with you from Stockholm and from the Center for Autonomous Systems. So some of the things I would like to talk about today, for some reason I cannot, go to the next slide. Okay, thank you. So most of the robots that we are seeing today have, apart from the ability to autonomously navigate in the environment, to also interact with the environment in different ways. Now, just to show you the first video of how, for example, a human washes dishes, I think that you will very soon understand why we still have a long way to go. Now just give it a look at what human does with the hands, how it very dexterously interacts with a number of different objects and also uses objects to manipulate other objects. And, just looking into this video, this is maybe not a task that most of us are anymore doing today, given that we use dishwashers. But lots of daily interaction with the environment is on that level. It requires us to use our hands, basically also the whole upper body. And the robots that we have today, both in labs and what is available in the market, are not able to do anything close to this. So what are the challenges that we still need to address, and what are the open scientific questions that can give us the ability to, in the future, have robots that can demonstrate something in this direction? Now, in our lab, we are working with a number of related problems that have to do with scene segmentation, interactive perception, object categorization, and so on. You see all on this on the slide, and some of these I would like to present in more details today. Now, grasping in realistic scenes. You have just seen a video, and what are the problems? What are the open problems? So we still need to deal with rather noisy data. It is in many cases very difficult to say what an object is. When interacting with the object, I'm just thinking here about grasping. There are usually many grasping and hypotheses. Any object can be grasped in infinitely many ways. And in most cases, parameters such as friction, mass, scene embodiment task, and so on are not known a priori, and these can also change during the time. So go back to the video of washing the dishes. The friction will definitely change once the water comes to an object, or the let's say the washing powder. And then lots of research in robotics has been oriented on learning from experience, but the big question is what and how to represent. What are the important parameters that we need to deal with? Now, in the next video, this is just what you would get from a regular Kinect, which is a very popular sensor for most of us to use today. And you see that even if we are able to reconstruct lots of the environment from the 3D perspective, there are still very many spurious measurements, there is lots of noise, and there are still parts of the environment that are not so very easy viewable or detectable by the robot. So in the same way as humans move around when they are not able to, let's say, see a whole scene, the robot will need to do the same. So in everything that we do, and what robotics and why robotics is different from computer vision, is that all the sensors that we are using are actually embodied, right? So we can, by moving robot's body, also get a better control of how and what we observe from the environment. That gives us a plus, right? Because we can get better data, but also it's more data, and we need to make sure that this data is also relevant for the task. Now I will show you just very shortly the next video, which just demonstrates another type of a visual system that we work with. This is an actuated humanoid head from KIT in Karlsruhe. And this is a dual binocular system. So there are two stereo systems, 4 eyes in total on the head. And here we just use regular cameras, 2 for peripheral and 2 for foveal vision. And what this head is able to do is to, in a way, mimic human ocular motor system. So the cameras can verge, the neck can pan and tilt, and so on. And in the next video, you will just see an example of how scene segmentation can be performed and what we mean by scene segmentation. So here we have a tabletop scenario with a number of simple objects on them. And what the robot does, it basically fixates its eyes on different objects in the environment. And in real time, so this is not speeded up, in real time, extracts hypotheses about what's on the table. So it builds a 3D model, segmented model of the object on the table, and this is the white line that you're basically seeing. So in a very similar way as a human, robots could also just move about in the environment and make these hypotheses about objects. Now, how do we do that? I'm not going to go very much into the detail of the theory, but just to give you a little bit of an example, what kind of assumptions we need to do in order to be able to achieve this real-time performance. And why is real-time performance important? It is very important because lots of the things that we want robots to do are very dynamic. And in order to be able to cope with dynamics, the perceptual data also needs to be both acquired and processed in real time. So in this case, how we model the system, we have a number of measurements, which is positions, disparities, colors. So we work in 3D. And the labeling, as we assume for our scenes, we say that, well, there is some foreground, there are a number of objects in the foreground. There is some background, such as, for example, a tabletop, because most of the objects will be put on some supporting surface. And there will also be another parameters. We can have a third one, which is, for example, everything that is not of interest. So we talk about that as a background, and flat surface is just then another model. Now the process is probabilistic. We basically have the goal of maximizing the probability of measurements and labels given then some incremental process. And again, all the details are in the paper that you see cited at the top. And estimation of the model parameters then is just maximizing over all combinations of models of measurements and labels. And for this purpose, we use a two-step process, which is very similar to expectation maximization by using a belief propagation. So what we do, instead of looping over all labelings, we loop over all labels, assuming that they are independent. And this way, we get a system that is less complex, and that it can be very nicely implemented in real time and give the results as you have just seen. So basically build hypotheses of objects in real time. Now, most of the things that we also do, or would like robots to do, as I said, certain assumptions about the environment. Now, whether the assumption that all the objects in the environment are put or are placed on some surfaces, supporting surfaces, not so much things are actually hanging from the ceilings apart from the lamps, we can assume that a top-down process is a good way to go. However, biologically seen, this is not maybe always what all systems do. So in my lab, we have been also looking into so-called bottom-up systems. And what does it mean to have a bottom-up system? Now, I will just go through the next video where you will see, for example, there are two objects, again, a tabletop scenario observed by a stereo set of cameras. And what we do here, we extract two groups of pixels that somehow are in the neighborhoods of each other's and also have some similarity. Those similarities can come from geometry or from texture. Now, once we do that, we can do different types of groupings. We can group pixels to small patches. We can group pixels or these small patches to 3D surflets. And without actually knowing what an object is, we can try to use this reconstructed information to test different types of grasps on objects. And this is exactly what you're seeing. So the robot doesn't know what an object is. It just has this patchlet-like representation of 3D, and it's using that to apply very simple grasps to random configurations of these. And the idea is that once the robot gets a hold on of the object, it can try and test what an object actually is. The way that we are demonstrating now this grasping in simulation is because we want to test how likely it is that some of these patchlet-based grasps will work without having actually any knowledge, again, of what an object is. Now, this bottom-up system can then be developed further, and this is what we did in our subsequent work, where an object, where the robot gets a hold of an object and then moves it under a control set of movements in front of its eyes and build a much better model of an object. Now, this would be definitely a suitable approach when the robot does not have a knowledge of all the objects that are available in the world, and it's through this interactive perception trying to find a way of how to interact with unknown objects. So going to the next slide, how do we talk about then grasping? We can stop the video and so what is a good grasp? How do we define a good grasp? I think that this is a very interesting question, and I think that many people have been working on this for quite some time. Now, a good grasp is maybe a stable grasp. So a grasp that once a robot puts its fingers around the object, it can move it, right? It can move it by safely keeping it in the hand. Now, if the robot is to interact with a human, just having a stable grasp is not maybe the major thing. The robot should maybe both be able to grasp the object stably, but also, such as in this case of handing over an apple or a glass, it should leave enough space for the human to take over the object. That would mean that there needs to be some balance between a good grasp in terms of stability, but also a good grasp in terms of some interactive properties so that a human can safely take over that object. So how do we get that information in the system? Now, it is very difficult to, in this cases, get inspiration from humans. We have had several big projects where we have tried to look into experiments with psychologists and neuroscientists and try to understand how humans plan their grasps. But it's very difficult. And most of the research that we are still seeing in the area of neuroscience, of psychology, actually look into very simple type of grasp. Like in this example, this is pretty recent work, maybe 2 to 3 years old. These are the examples or the experiments that are state-of-the-art in psychology. So human subjects are usually given example objects, and the task is to move the hand towards the object, so to grasp it. So what we can measure is, for example, where humans look, so what they fixate in, and where they put their fingers. So the information that we can get states that when a human is grasping something, the position of the eyes or of the focus will correlate with where the person puts his or her thumb. Now, how we can go further with that actually remains as an open problem. How do we design more, let's say, complex experiments where we also look into interactions between, let's say, humans and robots or humans and humans in terms of then exchanging objects in their hands? That would be one of the open issues that would be interesting to see in the future, how to do that. Now, lots of research in grasping has also been done on assuming almost no prior information, as I said, about objects, but also not about the grasp that can be performed on them. So the idea is that we have a fully data-driven approach where we just build a big database with some example type of objects. And for each object, we, let's say, label one part of the object that we call a good part of the object to grasp. And then different types of machine learning approaches can be used in order to, let's say, detect a grasp-like features in an arbitrary image without actually, again, knowing anything about the object. Now, although this is a pretty interesting approach requiring almost no understanding of grasping, it still requires a pretty long process being done after these initial pictures or features have been detected. And this is all grasping needs to be done in 3D. And some information about the 3D and the scene needs to be there. So approach like this may give you an idea of where potentially you would like to move, but in order to be able to move, a 3D is necessary. Now, we have worked further with that and also looked into the problem of so-called task-based grasping. So robots will usually, in a similar way as humans, need to interact with objects and grasp them, not because just they need to move them from A to B, but because they need to use an object for a specific task, okay? And this is really, really important because in case of humans, how we grasp objects depends on what we are supposed to do with them in the subsequent action or action subsequent to grasping. Our work on that has been looking then into some typical tasks such as handing over, pouring, dishwashing, and so on, or tool use, trying to understand where the fingers should be placed and in what configuration. And we have looked into that problem with different types of hands, for different types of hands, robot hands. Now, in order to be able to build a system, I just wanted to give you a little bit of an idea how complex it can become, even for a very simple type of a problem. Now, let's say that we talk about object features. So this is, let's say, something that we can extract from the sensory data about the object. Let's say that we have action feature set, which is, for example, types of grasp that can be applied on an object, which is related to the kinematics and dynamics of the hand. And then we also have some additional sensing in the hand that can tell us something about where the contact and what kind of contact occurred during grasping. How would we then go about that and build a system that let's say, answers questions such as, for example, given that object and a specific task, what type of grasp should I choose? Or given that I see that the human has, for example, applied a specific grasp on a specific object, can I predict what the human is about to do with an object? So we have modeled this with Bayesian Networks, then a graphical probabilistic model that gives us the possibility, once trained, to ask different types of questions. And questions that have to do either with what kind of grasp should I apply, or when a robot is observing a human doing or performing grasping, what is that human intention? What is the human about to do? Now, in order to be able to implement that, it is also very important to know what kind of questions we can ask or what kind of questions we can answer. And just if you now look into the first sentence or the title basically of this slide, robot bring me something to drink, or robot bring me something to drink from. it will actually require different type of decision making and different type of conditional probabilities to be estimated, stating that something to drink is different than something to drink from. Now, to show you a little bit how the whole system looks like and what's in the system, there is, of course, then in the bottom there is this trained Bayesian network that correlates or provides conditional probabilities between different types of measurements that we can make, knowledge about robots, kinematics and type of the hand, and also the information about different types of tasks. And for each object that a human or a robot would like to manipulate, it gives the information what is the best or the most likely grasp that should fulfill or that fulfills that specific task. And the probabilistic model can give us, let's say, some form of a probability distribution then that is pose dependent on the object, so that the robot can use this pose information when it plans its grasp. And the good thing about this is that now this approach is also integrated easily with the initial scene segmentation that I have showed you in the beginning, so that if there is a scene with many objects being then presented to the robot. Let us take this scene. It is very similar to the Kinect scene that I showed you in the beginning. And what you see here are two cups, a screwdriver, and a bottle. The question now is what kind of probabilities or output this Bayesian network system would give if the robot is to find something that affords pouring or something that affords tool use. So what you see is this kind of probability distribution being drawn or generated around each object in the scene, and the lighter the color, the higher the probability that that specific object affords the task, the required task. So we see that pouring is something that is afforded by two cups and a bottle, but the probability for the screwdriver is very low because it's shown as dark. However, the situation in the case of tool use is completely different. You see that the most likely object that affords tool use will be the screwdriver. Now, these are, as I said, interesting problems that can be then further developed and also considered more in different types of temporal frameworks. I am not going to go and present you more detail about the visual system, but some of the problems and some of the interesting things one can continue to work on is how do we understand really different types of categories of objects, given that many objects in the environment geometrically and also texture-wise look very similar, but afford very different types of questions, different types of actions. So, for example, a screwdriver and a carrot seem very, very similar visually in terms of texture and so on, but are very different objects. And these are some of the things that robots still have difficulties in understanding and dealing with. So from computer vision perspective, this is one big open problem that people need to address. Now, once we know what we see in the scene and what kind of grasp should be applied on an object, there is still a long way to go, I would say. And the reason is that, well, there is still lots of uncertainty when then a robot executes its grasp. And one of the things we have been working on for quite a long time is how to assess stability, not prior to grasping, but while a grasp is being executed. And the only way of doing that is really to employ tactile sensing on robot hands. Now, these are just two slides that show you examples of how tactile sensors on the shank hand feel or look like when they are interacting with the object. if we want to now use this system and let's say somehow learn from it, one of the things that is important is how can we generate enough training data so that we know how stable grasps feel. To be able to do that, we need very good simulators. So we need simulators that are also able to, let's say, generate good physical simulations of dynamics of two bodies interacting, and hopefully not only rigid bodies, because most of the hands that robots will use will be also equipped with some, let's say, soft pads at the fingertips. So there is still a lot to go there too. Now, one of the things that we then did is that we looked into the problem of how task-based grasp adaptation can be done with respect to, let's say, being able to also get feedback from the haptics on the fingers. I don't have too much time now to give you all the details, but this is just a couple of examples of how a Bayesian net can look like for different tasks. So the structure is going to be different, and we are looking into the different types of structures and how these are used for different tasks. And then almost the last movie that I have here, we can then take the next one. We'll just show you how then the whole system can look basically once a robot starts to interact with the system. So let's say we have an object in the scene, and we would like to implement or test the test the grasp for a specific task. The system that is based on Bayesian net can plan a specific grasp and choose whether this is a good or a bad grasp for the task. We can also predict the likelihood of that task being stable or not. And this was just for the demonstration. The Bayesian net said that this would be an unstable grasp, but we just tested it to confirm. Now Bayesian net is saying that that should be a stable grasp, because what tactiles feel is it feels like a stable grasp. It's in the light region on the fourth image here, and the robot can then safely pick up the object and use it to pour out the fluid from it. And all of this can be done in real time, but again, it does require lots of training data to be generated and to be tested in real scenes. Now, just for the final 5 minutes, I also wanted to take a little bit of your attention because there are too many slides left and I can't go through them. That what really is also the interesting problem for the future that is related to grasping, but it's not really doing the classical grasping as we commonly see it in terms of generating solely stable grasps. So sorry for going a little bit faster now through these examples. I just want to come to a couple of images where we see images like this. For example, how should a robot operate scissors, or this teapot, where not necessarily we can generate type of stable grasps that we are classically used to see in most of the, let's say, robot grasping examples. So what we do in this case, we use so-called the topological object features and topologically inspired robot hand representation, where we then rely on some classical mathematical notions from the topology, where we talk about, let's say, links and lines that are, or closed curves that are interacting. Now, let's say that you have a hand with 3 fingers, and that there is a on the pot there is a handle where we can detect loop. How can we now define and design different types of control algorithms where we put two links in interaction. So you have something like a chain. This goes back to caging. So we are defining cages between objects. And why is that interesting? It's interesting because holes and loops are everywhere on most of the objects that we have, and most of the classical grasping algorithms just based on pure stability estimation won't work. So our recent work is then looking into how we can detect loops in point clouds and how we can also then by using topological features, so this is a work from this year presented recently at both IROS and also humanoids, how we can use then these topological features to define different types of cages that allow not only to have hold of an object, but also to apply actions such as lifting or pulling or hauling and so on. And there are many examples of how we can do that on also very noisy point clouds and so on. If you're interested in the details, I would then suggest that you go and look into these files, the publications that I have here. I would just like them to finish up and show you the last video that shows how some of these grasps can be nicely generated on a now robot, which is very difficult to work with because it's not very dexterous and it has a very, very small workspace. So what you see here is a three-fingered now hand basically then making a chain that chains the handle of the basket. And what is interesting is that we can then generate some classical grasps, like in the first two examples, but that we can also consider an upper body of the now, and then to chain the object with a hand that passes through the handle of the object. And I think that that gives you also an idea how we could go further with that and how we could also, for example, in the future use robots to, let's say, use caging and not classical grasping to work in 3D. Okay, I think that I will stop here. There are a couple of more interesting things that we are working on. But I think that to summarize, active vision and attention are really important problems to solve because we need to have a good understanding of the environment in order to be able to interact with it. And then when interacting with the environment, we need to address the problem of grasping and caging in a task-dependent manner. For those more interested, there are a couple of slides, a couple of publications at the end of my publication that you can look at, and here is also thanks to all my collaborators and my financiers. Okay, thank you so much. This was the end. I don't know if there are any questions.
Thank you very much for your presentation, Danica. So the floor is open for the global audience. If you have any questions, please just open your microphone and maybe say which side you are, so I can put you on the big screen.
From Madrid.
Madrid, please go ahead.
Yeah. So far we've seen your work with our robots, traditional robots that are more rigid, but have some soft parts of the fingers, for example, and some soft pads. How do you think the grasping will be simplified when we're able to use platforms that are softer and are able to passively adapt to, for example, whatever you grasp with the hand?
I don't know if anybody else heard the question. I had very...
Your microphone is very, very low, Madrid. Could you turn up the microphone a bit?
Okay, can you hear me now? Can you hear me now?
Yeah, that's better.
Okay, perfect. So I just wanted to ask, how do you think moving to softer robots, so hands with more flesh-like structure, will simplify grasping in the future?
I think that that's a very good question to start with, and I think that it might simplify some of the problems, and we may not, rely anymore on the same type of the classical stability measures as we do now. But it will also, I think, require lots of kind of, data-driven approaches and experimental evaluation to basically see what the abilities are. And one of the things that will be interesting to see whether we will be, and to what extent, also build very realistic simulators so that maybe we don't need to test everything with robots. And I think that this has been one of the big problems in robotics, to actually have soft contacts and soft body interaction actually being developed very realistically in simulators. But I think that it will definitely simplify lots of the problems. Now, whether I think that only having soft bodies is enough, no. I think that one of the important problems is also to think about the dexterity, right? Because even if you have a soft body, but only with 1 degree of freedom, yes, it will do better than 1 degree of freedom rigid hand, but the dexterity is also an important thing. And I think that, I believe that this is important because very little of the research that is being done right now considers in-hand manipulation. So how do we change the pose of the object in the hand? And I think that with soft structures, it will be easier to do that. But then in order to be able to, to demonstrate it, we will also need the dexterity. So both of these, I think, are important, and it will definitely change a lot of the grasping and interaction as we see it today. Thank you.
Thank you. And I think we have time for one more question.
Hello, Professor Korjik. This is He Sheng Wang from Shanghai Jiaotong University. Thanks for your talk. I want to ask about how you consider about the deformable object with vision to grasp.
So exactly. I think that I haven't had too much time, and the last part of my talk has been exactly on that topic. What types of grasps should we be considering about when talking about deformable objects? I think that one aspect of this caging that I have been introducing might be a good way of addressing that problem. So, lots of backpacks and bags and everything that humans commonly manipulate every day are actually deformable, and in those cases we are not really applying very stable grasp, but we apply cages. So that I think is one way to go. The other way to go is to have more understanding on the dynamics of how the object changes, a deformable object changes once a grasp is applied on it. And this depends not only on the surface or the shape of the surface, but also if we talk about objects such as, let's say, food containers, like, milk packages and so on, it depends very much what kind of material is in the container. So understanding from both visual but also tactile feedback, what is the viscosity, what is the, let's say, what are other dynamic parameters or attributes of the object is necessary in order to be able to devise different types of let's say, grasps or cages that will allow us interaction with objects like that.
Thank you.
Thank you.